let's move on to units of measurement. Okay, so um, units, what units do is they give dimension to and standardize a number. So what that means is if you said, hey, how tall are you? And I said 6, you'd be like, is that 6 inches? Is that 6 feet? It gives dimension to that. The way that it standardizes it is if you lined up 6 people and they're the exact same height, you would know that if one was 6 feet tall, the rest would also be 6 feet tall, right? Units are super important, and not including units is another mistake that I see a lot of students make. And so it's important to keep those there. Um, so we use the English system. It's also called the imperial system. In the US, we use feet, we use pounds, degrees Fahrenheit. If you have not been convinced that the metric system is a better system, this is going to do it. I'm almost positive. For example, if I asked you how many uh, cups were in a gallon, would you be able to tell me that right off the bat? Probably not. But if I asked you once you do this, you will instantly be able to tell me how many milliliters are in a liter. That is the beauty of the metric system. So we're going to be using a lot of different units in this class, and here are some of the basics. We have length, and we can measure that in meters. The symbol is a lowercase m. For mass, we use the gram, which is a lowercase g. For time, we use the second, which is the same as what we do in the imperial system. There's no difference there. Temperature, there's a couple of them. Kelvin and Celsius, just like the beverage. Kelvin is a K and Celsius is a degree C. You will note that Kelvin, K, does not have a degree symbol. We'll get into what Kelvin is in a bit. Amount, that's a very broad term, and so is the unit of the mole. We will also get into this, MOL. That is how that is categorized. And then finally, the volume, we have liters, that's an uppercase L. Now, I used milliliters and liters as an explanation or like as a example. Um, but how do we know exactly what that is? Well, let's show it. Let's do it. So we're going to start around this area right here. This is a big table that tells you about prefixes. Now, you are going to have to memorize these, unfortunately. I apologize if memorization isn't your thing. We will eventually do this to the point where you will have them memorized, kind of whether you want to or not, hopefully. But it doesn't hurt to get a jump start on it. But for this, we have we'll start with deca. So deca, you can think of like a decade. That is going to be 10 to the first power. So 10 to the first power, that is 10. Anything to the first power is the number that it has, that the base is. So 4 to the first power would be 4, anything like that. So 10 to the first power is 10. Hecto, this is going to be 100, like in hectare, 100 square feet. That is 10 to the second power. Kilo, that is 10 to the third power. So once we get to three, we're going to start jumping things. Mega, as in megabyte, that is 1 million bytes. That is 10 to the sixth power. Giga, as in a gigawatt, that is 10 to the ninth power. That is a billion watts. Tera, as in a terabyte, that is 10 to the 12th power. Um, that is a trillion. So Elon Musk is the first person who just got a teradollar, basically, $1 trillion. You could also go down in scale. So deci, that is going to be like a decimal, a tenth. So 10 to the negative first power. Centi, 10 to the negative second. Milli is going to be 10 to the negative third. So like a centimeter is, there are 100 centimeters in a meter. Milli is going to be 1,000 millimeters in a meter or 1,000 milligrams in a gram. 1/1000th is how you would write that. Micro soft. I don't have one for that. I don't know. Micro aggression. I really don't have one. Is it 1/1 millionth of an aggression? So that's going to be 10 to the negative sixth. Nano. I like this one because it has nine basically in that. That's 10 to the negative ninth. Pico. Um, that sounds like my old dog. His name was Paco. That's 10 to the negative 12th. Femto, that is going to be 10 to the negative 15. Now, we'll probably very rarely use pico and femto, but these are measurements that are used in chemistry. Okay, so um, in order to use all of these things together, we're going to use dimensional analysis to kind of do this. So dimensional analysis is what we do to convert one quantity to another. We're going to take one thing and convert it to another. So you probably have done this before, converting quarters to dollars, converting, miles per hour. That's what we call a conversion factor. So two equivalent quantities. You could have 1 inch is equal to 2.54 centimeters. Um, and if you look back here, all of these values are going to go before the symbol of the physical quantity. When you want to talk about a centimeter, for example, you would write CM like that. So CM for conversion factors, these are going to represent exact numbers. So if you went uh 12.6 miles per hour like that, you would that would, or like, let's say that you, sorry, that example. Let's say for the 1 inch at 2.54 centimeters, these are exact numbers in that 1 inch will always be exactly 2.54 centimeters. Just like for 1 foot, there are going to be 12 inches. That's always going to be true. So we can say that they have an infinite number of significant figures. We don't care how many sig figs they have. Um, so these are the ways that we solve a dimensional analysis problem. First, you want to recognize what units you're converting from and what units you're converting to. Um, and I like to do this thing called the train track method. So it looks like this. We're going to take this kind of a line, and I'm going to make a split in the middle like this. It's called a train track because if you were to look at like a map, train tracks are represented something like this. Um, Over here goes the units that you start with. These are your starting units. Down here are going to be the same as top left units. And that is by design. We'll see why in a second. Over here, these are going to be your ending units. So what that means is once we have this set up, we can start doing this train track method. We'll recognize what units we're converting from and what units we're converting to. If I wanted to take 2.5 feet and convert that to inches, that would mean that my starting units are feet. So I'll put an FT right there, feet. Um, my ending units are going to be inches. So IN right there, feet, and then inches. Now, whatever goes on the in the top left needs to go on the bottom. So feet on the top left, and then feet has to be on the bottom as well. So we recognize what units we're converting from and what units we're going to. We set up the conversion factors that allow for these units to give desired results. Now, this is going to be where we put the conversion factor. We're going to start plugging in numbers now. Our conversion factor right here says that 1 foot is going to be 12 inches. So what we'll do is we will say 1 foot, whatever the foot one is going to go down there. 12 inches is going to go on top. The other thing that we have is our starting amount to go with the unit. So feet is on the top left. 2.5 is going to go in the top left along with feet. And so we're left with this kind of thing right here. What we're going to do then is kind of collapse it. Everything that is on the top is going to get multiplied together. Everything that's on the bottom is going to get multiplied together. Now, this is empty for a reason. There shouldn't be anything down there. Most times you do this, there will not be anything in the bottom left of this train track. So that's okay. You can just ignore that. Um, we're going to kind of collapse these. But first, let's take a look at the things that are canceling out. We have feet on top and feet on bottom. You could think of it like a fraction. If you have the same thing on top and bottom, those cancel out. And that's because this is a fraction. We're about to make one. Inches is not on the bottom, so we'll keep inches. And it ends up being the unit that we want. So we'll end up with this 2.5. We're going to make this into a fraction. Multiply everything on top by each other times 12. And we'll divide that by the number on the bottom, which is just 1. We can imagine that this is a 1 here and it has no units if you'd like. But really, you can just ignore it if there's nothing in this box right there. That's okay. But 2.5 times 12 divided by 1, that gives us a value of, I'm gonna put it up here, 30. Now, the units that go with it are going to be the units that were not crossed out. So that's going to be inches. So 30 inches. There we go. Okay. So you can do a train track with many different values in between. Go ahead and try this one. We want to take centimeters and turn that into meters. So centimeters, um, for every 100 centimeters, there's 1 meter. So go ahead and give it a shot, and then I'll show you how it's done. Okay, cool. Let's do it. We have uh, 153 centimeters. We're going to put it into meters. So if we make this train track, it's just a simple one-step train track. We'll start with 153 centimeters. I'm going to fill in the units first because I need to know where they go. The conversion factor says that 100 centimeters equals 1 meter. So um, I will put in the um, centimeters on the bottom here. Centimeters needs to cancel out. Meters is going to go on top. Now I'll start filling these in. 153.00 centimeters. We have 100 centimeters and 1 meter. We then will multiply everything. Oh, we'll cross out units. Make sure we're going to be ending up in the correct units. That is correct. We want to convert to meters, so that's fine. We will then have 153.00 multiplied by 1, divide that by 100. Now, I did forget on the last one to do this, so I'll do it here. But how many sig figs should we have on this? That's going to be um, whatever was measured. So this is our conversion factor. Conversion factors are infinite sig figs. We don't care how many sig figs they have. They have enough for us to only care about our measured one, which has 5 sig figs. Now, the number we get out of here is going to be 1.5300 meters, like that. This is our answer for this, and with the correct number of significant figures. These are trailing zeros after a non-zero number, and so those are significant zeros. Um, and we can keep going. So let's try this one over here. Actually, before we do that, let's go back and see how many sig figs are we going to give for our answer? Well, let's take a look. The sig figs that we were given in our measured value was 2. How many sig figs do we have here? Currently 1. So we need to change this in some way so that we have 2. There's 2 ways we can do it. The first way, put a decimal point right there. Nothing after it. That just tells us that this is a significant zero. The other way is we could say 3.0 times 10 to the first inches. Now, this looks a little silly. I mean, they both kind of look a little silly, if I'm being honest. It's like so many more characters to write out. That one is. And this one just has a decimal place. This one always feels weird for me to write, but it is technically correct. Both of those are correct. Let's go on to the next one. Okay. So if we wanted to convert 280 centimeters to feet, we would need a couple of different values. So um, go ahead and take some time right now to go back to uh, no, we don't have that. I will help you out with this. A little bit of cutting can go on there. So if we want to stick 280 centimeters to feet, we know that um, 1 foot is 12 inches. We know that 1 inch is 2.54 centimeters. We can use this data. So 1 foot equals 12 inches. 1 inch equals 2.54 centimeters. And actually, let's go ahead and do this over here. So if you have a multi-step equation where you need to go through many different instances in order of the train track method in order to get to your answer, you might want to do it this way so you can kind of keep track of things. First, write out where you want to go. We want to take 280 centimeters and convert that to feet. So our desired conversion is going to go right here. You have centimeters. We're going to turn that into feet. Our conversion factors are going to be that 2.54 centimeters um, goes to 1 inch, and there are 12 inches in oop, inches in 1 foot. And so we could even say 2.54 centimeters to inches to feet. So centimeters to inches to feet. Now we have a general roadmap of where we want to go. And that is what we can call our solution map. Our solution map is going to be how we get where we're going. Then let's solve the problem. We're going to do it in a train track just like we did before, but this time, instead of just the 1, we're going to put 2, like that. So we'll start with what we have. That's going to be centimeters. We know that we need to convert centimeters to inches. There is a conversion of centimeters to inches right there. Since centimeters is in the top left, it has to go in the bottom right. So centimeters goes on the bottom, inches goes on the top. And then to get from inches to feet, we will do that as well. So inches and then feet. Uh, Inches has to go on the bottom right because it goes in the top left. Now we can plug in our values. 280, put that decimal there to make sure we have the correct number of sig figs. For every 2.54 centimeters we will have 1 inch. And for every 12 inches, we will have 1 foot. Cross out all the units that are the same in centimeters, inches and inches. And so feet is the only thing left. We are left with 280 times, I'll do this, times 1 times 1. We will divide that by 2.54 times 12. And that gives us the value of 9.186 right there. And so the only unit that's left over is feet. Let's trim it by the number of significant figures we need. 6 is greater than 5, greater than or equal to 5. And so we will raise up that 8, and then we end up having 9.19 feet. And we're done, just like that. Okay. So, what if you get solution maps with raised powers? Like, what if we need to convert from cubic inches to cubic centimeters? There's a couple ways you can do this, but um, this is one of them. So, 1 inch is equal to 2.54 centimeters. We've covered this so far. If we cube everything here, we end up with 1 to the third inches is 1 to the third cubic inches is equal to 2.54 to the third cubic centimeters. And so that ends up being 1 times 1 times 1 is just 1. So that's going to drop down. 1 inch cubed is equal to 2.54 cubed, which is 16.39. Now remember, this is a conversion factor, so it has as many sig figs as we need. So we'll just put another one there. And so that's basically how you go about doing that, is you just cube whatever the number is and the unit. Um, you can also do it like this. If you want to make a train track about it, this is maybe not the easiest way because it can get a little confusing, but let's say that we put 3 down. I will put 1 cubic inch on the top left, and I will convert from inches to centimeters 3 times in order to get rid of that inches cubed. So 1 inch is equal to 1 or 2.54 centimeters, just centimeters. We'll do that again. 1 inch is 2.54 centimeters. 1 inch is 2.54 centimeters. That ends up with, for every time there's an inch on the bottom, we'll take 1 away from the inches in the top left. So that ends up being inches, inches, inches. That's 3 of them. We end up with just that. All 3 of these are gone. And we have centimeters, centimeters, centimeters. We'll multiply those together and we end up with 2.54 times 2.54 times 2.54 divided by 1 times 1 times 1, which is the same thing as 2.54 cubed, which is 16.39 cm3. Just like that. Okay, this is the last thing, and I'm just going to lump it in here because we're almost done with these slides. Does every object have the same with the same volume have the same mass? So if you had a soccer ball and a bowling ball that had the exact same volume of 5,400 cubic centimeters, what do you think? I would say that the bowling ball is definitely going to be heavier. So no, they do not have the same mass. And that is because they have different densities. So density is what is called a compound unit or a combined unit. And that's when you have two different units multiplied by multiplied or divided by each other. Density is equal to mass times volume. And I remember it like this. Density is equal to this. I'll draw a little heart like that. And you have an M on top and you have a V on bottom. Density is equal to mass over volume, just like that. Okay. And so because of the density, they have the same volume, but this one has a higher mass. And so, because the bowling ball is more massive in the same volume, it ends up being more dense. Now, if we wanted to find um, the mass of a ball uh, that had a certain volume and a given density, how would we do it? Well, let's go ahead and try it. So, we do know from before we can use 1 inch cubed uh mul it is equal to 16 point, what was it? Let's take a look back. 39 centimeters cubed. 39 centimeters cubed. And we can use that as a conversion factor. We can set up one of these train tracks and we can say 33.5 inches cubed. This is where we're starting with, right? Um, we can then use this conversion factor to find the amount of density that we need, or the amount of volume in cubic centimeters. We can then use cubic centimeters to convert that to grams. And so 13.5 cubic inches for every 1 inch cubed, we have um, we have 16.39 cubic centimeters. Now, this 4.2 grams per cubic centimeter is basically the same as saying 4.2 grams equals 1 cubic centimeter. That's because it's per cubic centimeter, meaning for each cubic centimeter that you have, you will have something that weighs 4.2 grams. So this is our next conversion factor. We need to cancel out units. So 1 cm3 goes on the bottom and 4.2 grams goes on top. We will then multiply the top, divide by the bottom multiplied. That's 33. Ooh, 33.5 times 2 point, oh, sorry, times 16.39 times 4.2. Divide that by 1 times 1. And just to be sure, before we actually punch all this in, uh, inches cubed cancels out, centimeters cubed cancels out, and we're left just with grams right there. This ends up giving us the answer 2,305.66 grams, um, which when we adjust for two significant figures right there, or three. This would be our measured value. This would be three sig figs here. Um, we will end up getting 2,310 grams or 2.31 times 10 to the third grams. Either one is okay. All right. So this one asks you to take it a step further. I'll let you try this on your own for just a second, but for this, I want to give you something else. So what is the length of what is the length L of one side of the cube that has this density and this mass? Um, if volume equals length cubed. So to get rid of length cubed, there's a shortcut you can use. If you have a scientific calculator, there will be a button that looks like this, most likely, or with an X that you can put a 3 into instead of that. Um, Go ahead and solve for A, then put whatever value you get for A, uh, take the cube root of it, and you will end up getting your answer. Okay, try it out, and then I will show you how it's done. Okay, so let's see. Where do we need to go? We need to go from kilograms to cubic centimeters. And we can do that like this. Kilograms goes to grams, and that goes to uh, cubic centimeters. Kilograms to grams, that's a conversion that we have seen before, which I will go back to. Grams to cubic centimeters, that comes from the density right there. So we'll set up a train track to figure this out. We'll start with our kilograms because that is our unit that we have all by itself right there. So kg. We can then use um, a conversion. So we need to have kg on the bottom, and we're trying to go to grams next. So grams has to go on the top. Then we need to go from grams to cubic centimeters. So grams has to go on the bottom, and cubic centimeters goes on the top. Now, sometimes this can happen where it's grams divided by cubic centimeters, but we have to put the grams on the bottom. This is a common occurrence. It will happen. Um, Keep in mind that we can make this into an equivalency instead of a fraction, where we can say 2.3 grams is equal to 1 cubic centimeter, like that. So we'll start with what we have, 2.25 kilograms. Now, kilograms and grams, for every 1 kilogram, there are 1,000 grams. This comes from, where is it? This right here. Kilo gives you 10 to the third, which is equal to 1,000. Um, and so we will use that. Uh, if you're ever confused about what goes where, the large value or large unit, so kg is a larger unit. Large unit is always going to go with the smaller number. Um, and vice versa. The small unit, grams, is always going to go with the large number. Okay, then we can use this equivalency. 2.3 grams for every 1 cubic centimeter. This gives us an equation where we have 2.25 times 10 or times 1,000 times 1. We'll divide that by 1 times 2.3, and we are left with a value of 978.26. Um, that would be centimeters cubed. We can change we through the power of sig figs, we will make that into 9.8 times 10 to the my bad 9.78 9.78 times 10 to the 2 centimeters cubed. And I knew that I needed to do that because this is a conversion factor. So we're going to let that be the number of units or infinite sig figs. This, however, is our measured unit. And so we will have this be our answer. 9.78 times 10 to the 2. Now, as I said before, we're going to just use the cube root to get what that length is, the length of one side of this cube, right? The cube is going to be uh the this is your H, this is your W, and this is your L, or your I guess lowercase l. That's your length times width times height. For a cube, those are all equivalent, so that ends up being length cubed. So what we can do is we can take the cube root of 9.78 times 10 to the 2, or of 978. And that ends up giving us a value of 9.93 centimeters. If you cube root the number, you have to cube root the unit too. Um, and we are finished. And that's it. Okay. See you in chapter 3.